So now we are going to see the topics registers, shift registers and shift register counters. These are the topics we are going to see in the third unit. Okay, the topics are registers, shift registers and shift register counters. So in this going to study the introduction, buffer register, classification of register, shift registers and their modes, bidirectional shift register, universal shift register. So first introduction. So register is an important application of flip-flop. What is flip-flop? Flip-flop is 1-bit storage element. So if you want to store more bits, then we need more flip-flops. The groups of flip-flops is known as register. What is register? Register is nothing but group of flip-flops. So in order to store more bits, we will be using more flip-flops, and the combination of flip-flops is nothing called register. So an n-bit register will consist of n number of flip-flops. Now buffer register. So buffer register is nothing but it will just store and give the output. So it will not do any modification. Just for time delay, you will be using this buffer register. So it is this buffer register is constructed by D flip-flop. We'll be using D flip-flop for buffer register, and the type of flip-flop what you have used is positive edge triggered flip-flop. So I already told you that what is triggering. Triggering is nothing but making the flip-flop to change its status called triggering. There are mainly two types of triggering, that is level triggering and edge triggering. So in the edge triggering, there are two types, that is positive edge triggering and negative edge triggering. Now, the operation of buffer register, the data to be stored is B3, B2, B1, B0, and we are taking the data as 1010. Here we are using 4 D flip-flops and we are applying clock, and the corresponding output will be 1010. This buffer register will give the same output as the input. Okay. Now, this is the diagram of buffer register. It is having four inputs, B0, B1, B2, B3, and we are using 4 flip-flops. The type of flip-flop what you are using is nothing but the D flip-flops. Okay, and we are giving common clock, and the type of flip-flop is positive edge triggered flip-flop, and we are giving the input 0, 1, 0, 1, 0, 1. So this is the input what you are giving from the MSB. If you are telling 1, 0, 1, 0, this is the input what you are giving. Then we are providing the clock. So while providing the clock, you will be getting the output. The same output you will be getting. Okay, this is the output. So 1010 is the input what you are giving. Then we are providing the clock so that you will be getting the output. So this is nothing but buffer register. Register is nothing but the group of flip-flop. So next we are going to study shift register. So shift register is a multi-bit register. It will be having more than one flip-flop, and its function is to move the bits right or left depending upon the clock. Depending upon the clock pulse, it will either shift right or left. Now, classification of shift register. Shift register is classified into mainly first 4 types, that is serial in, serial out, then serial in, parallel out, then parallel in, serial out, then parallel in, parallel out. In serial out, there is 2 types, shift right and shift left. Okay, these are the modes of operation of shift register. What is shift register? Shift register is a register. It will shift the binary data right or left depending upon the clock pulse. Okay, now flip-flop, shift register and its mode of operation. First one, serial in, serial out shift register. That is shift right. Serial in, serial out. There are 2 types. One is right, shift right. Another one is shift left. So serial in, serial out means you will be giving the input in serial one by one and you will be getting the output one by one. So this is shift right. So data bits are shifted from left to right by one position per clock. For each clock it will be shifted by one position. Then serial in, serial out, shift left. Data bits are shifted left by one position per clock cycle. Then serial in, parallel out. You will be giving the input in serial and you can get the output in parallel. That is serial in, parallel out. Here all the outputs are made available simultaneously after the 4 clock pulse. Here after 4 clock pulse you will be getting the output. But in the case of shift serial in, serial out, we will not get the output after clock pulse. Here we need 8 clock pulses. Okay. Similarly, parallel in, serial out. Here all the inputs are applied simultaneously after 4 clock pulse simultaneously, and after 4 clock pulse output is available serially. Now first one, serial in, serial out, left shift shift register. In, serial out, there are two types. One is left shift and another one is right shift. What is serial in, serial out? Input is given in serial one by one and output is also got one by one. So this is the circuit diagram of your logic diagram of your serial in, serial out shift register. Here you are having 4 D flip flops and you are applying clocks to all the 4 flip flops, and the type of triggering is nothing but positive edge triggering. Before the application of clock pulse, what we are having is nothing but output of each flip flop is 0 0 0. Now after the clock, on the first falling edge of the clock, the flip flop 0 is set and stored data in the register. So this is the input what you are giving. Serially you are giving. First input is you are giving 1. During the first clock pulse, this 1 will be coming as output. Next again you are providing the input as 1. So already the 1 which is here, it is shifted to already one which is present here is shifted to here, and the input it is coming to the output. Now during the next clock pulse, the one which is here it is shifted to this position, and the one which is present here is shifted to this position, and this input it is coming to the output of the first flip flop. Then we are applying the next we are applying the next clock pulse, next clock pulse and the input. So we are, it is shifted one bit left, so the data 111 has come out, but in order to get all the data you need 4 more clocks. So this is a summary of shift left operation. Initially it is 0 0 0 and this data is shifted left by one position, this data is shifted left by one position, this data is shifted left by one position, and you are providing the input 1 for the first clock pulse. So this one will be coming as the output. Next you are providing the one as the input, so this one will be coming as output, and this one it is in the output, it is shifted here, and this 0 it is shifted here, and this 0 it is shifted here. Similarly during the next clock pulse you are providing the input as 1, so this one it is shifted here, and this one it is shifted here, this one it is shifted here, and this 0 is shifted here. Similarly during the next clock pulse, this one will be shifted here, this one here, this one here, this one here. So after 4 clock pulses, the output of the 4 flip flops will be 111, and if you want to get the entire output out of the last flip flop, then you need 4 more clocks. So this is serial input, serial output, shift right. So here you are giving input to the left, there we have provided the input to the right. So now when you are applying clock pulse, you'll be getting the output. So next one is serial in parallel out. So here you are providing the input serially and you are taking the output. So here you are providing the input serially. You are providing the input serially and you are taking the outputs parallelly. So at that time you are taking the output here. So previously serial in serial out, here serial in parallel out. So number of cycles required to load the 4 bits is you need 4 clock pulses. So the speed of operation of serial in parallel mode is same as serial in serial mode, but the output you can get after 4 clock pulses. But in the case of serial in serial out, you need 4 more clock pulses to get the output. Next one is parallel in parallel out. Here we are providing the inputs in parallel and similarly we are getting the outputs in parallel. So here you will be getting with one clock pulse you will be getting the you can load the all the bits and in the next clock pulse you will be getting the output. So during the first clock pulse data is so during the first clock pulse this is parallel in parallel out. So during the first clock pulse we are providing the inputs and during the next clock pulse we are getting the outputs. So I will show once more. So during the first clock pulse you are getting the you are providing the inputs and next you are getting the outputs. Only one clock is essentially load all the bits and you can get the output. Okay. Now parallel in serial out. Here you are giving the inputs in parallel and you are giving the input in parallel and getting the output in serial. There are two modes. There is one is shift mode or load mode. So this is parallel circuit diagram of parallel in serial out shift register. Okay. So this shift bar slash load bar it indicates when you are giving 0 to this control input data will be loaded and when you are giving 1 it will perform shifting operation. Okay. So when you are providing 0, so I will explain this circuit clearly. Now we are giving 0. When you are giving 0, the AND gate 1, 3 and 5 it gets disabled. Why? Because it is connected to the line 0 that is shift this line directly. So you are giving 0, the 0 input is given to the gates 1, 3 and 5. So it gets disabled. Now the 0 it is giving going to an inverter and it will become 1. And the one of the inputs of 2, 4 and 6 is 1. And you are giving to the other input of the AND gates you have provided B3, B2, B1 and B0. And one of the input of these AND gate is 1. So the output of this AND gates depend upon the other input. If the other input is 1, you will be getting an output of 1 here. If the other input is 0, you will be getting an output of 0 here. Okay. So and for the first flip-flop, you are directly given the input. For the first flip-flop, you are directly given the input, and for the second, third and fourth, you are providing it through a AND gate and an OR gate. So this is nothing but loading of the data. So next what we will be doing is you will be giving a control input of 1. Initially we have given a control input of 0. When you are giving a control input of 0, what is happening is data is loaded into the shift register. So when you are giving 0, data is loaded in the shift register and in that time the AND gates 1, 3 and 5 are disabled and 2, 4, 6 are enabled. When you are giving 1 to the control input, the when you are giving 1 to the control input, the gates 2, 4 and 6 it gets disabled, because when you are giving 1 here, you will be getting 0, and one of the inputs of this gate 2, 4 and 6 are connected to this line, so it will be getting 0. So these gates 2, 4, 6 are disabled. Now while applying clock pulse, the input that is present in the B naught, it will be transferred to Q output in the first clock pulse. So you assume that B naught is equal to 1. So during the first clock pulse, this B naught will be transferred to this AND gate. Already one of the input of this AND gate is 1. So you take the data as 1, 1, 1, 1. So during when you're giving 0 to the control input, the inputs these gates 1, 3 and 5 is disabled, and we got the inputs to the input of this flip-flop. So you're having these values at the inputs of the flip-flops. So during the first clock pulse, this input 1, it will be transferred to this AND gate, and it will be coming to this flip-flop. Similarly, during the first flip-flop, the input what you're having here is 1. That 1 will be transferred to this output, and it will be coming to here. Similarly, at that time, this input is transferred to the output of Q2, and the output of Q2 will be transferred to D3 during next clock pulse. Okay, this is the operation of shift parallel, load shift slash load bar. So that is, it will be when you are giving the control input as 0, input is loaded, and when you are giving 1, the input is shifted. Okay, once again I am explaining the working. So this is parallel in, serial out, shift register. So when you are giving the input parallel and getting the output serial, so here you are having a control input shift slash load bar. The meaning of this is, when you are giving 1, this circuit will perform shift operation, and when you are giving 0, the input will be, first we will assume that we are giving an input of 0. So we are giving an input of 0. So in this black line, that is here, the gates 5, 3 and 1 will get disabled. Why? Because it is connected, the one of the input of these gates is 0. So this 0, after coming from an inverter, it will become 1. So the gates 2, 4 and 6 is enabled. Now to the other input of this AND gates 2, 4 and 6, we have connected the inputs B1, B2 and B3. For the first flip-flop, we have connected the input directly. So we have connected the input directly. So we can take the input as B0 is equal to 1, B1 equal to 1, B2 equal to 1, B3 equal to 1. So here directly we will be getting the 1 here. Now since this the one of the input of this AND gate 2 is 1, already it is 1, and this B1 1. So here we will be getting 1, and if one of the input of this OR gate is 1, so output will be 1. Similarly here, already on one of the input of this AND gate is 1 because it is connected to this line. So here it is 0. So here you will be getting 1. So B2 is 1. So 1 into 1, the output of AND gate will be 1. So if this is OR gate, if any one of the input is 1, output will be 1. Similarly here 6. So already one of the input is 1. Here B3 value is 1. So the output of this gate 6 is 1. Output of this OR gate is 1. Okay. So this is nothing but the operation which is occurring when you are giving 0 to the control input. Now you are providing 1. So what you are providing? Now you are providing 1. So you are providing 1 and already you are having the inputs 1, 1, 1, 1 here. Okay. When you are when you provided 0, the input has loaded into the shift register. Now I am applying clock. During the first clock, this 1 will be shifted to here. Okay. So shifted 1 I will write like this. This 1 is shifted here. And this 1 is shifted here. This one is shifted here. And this one is shifted here. So the first output we have got in the Q3. So during the next uh, uh, clock pulse, here the input is 0. We are not giving any input. This one will be shifted here. Again, this one will be shifted here. This one will be shifted here, and this one will be shifted here. How means this one? When you are giving 1 here, the gates 1, 3 and 5 gets enabled. What happens when giving 1 here, the gates 1, 3 and 5 gets enabled. So one of the input is 1. So whatever it is coming here, that will be the output of this AND gate. So if it is 1, both the inputs are 1, here will be getting 1. The output of the OR gate is 1 if one of the input is 1. So the bits are shifted right when you are giving an input of 1. This is nothing called parallel in, serial out, shift register. Okay. Now you are going for bidirectional shift register. Here also you are having a control bit M. When you are giving M is equal to 1, it will shift right. Similarly, when you are giving M is equal to 0, shift left. So first we will check M is equal to 0. So when you are giving 0 to this line, the gates that is connected red, that is 1, 3, 5, 7. These gets disabled. What happens? These gates gets disabled when you are giving M is equal to 0. So when you are giving M is equal to 0, it gets disabled. Now when you are giving 0 here, this line, it will be getting 1. So the one of the inputs of the gates 2, 2, 4, 6, 8, it is 1. So one of the inputs of gates 4, 6, 2, 4, 6, 8 are 1. Now we are providing serial input for left shift to the gate 8. So for example, you take the data 1. So you are applying clock. So what happens? Here you are having 1. So here you are having 1. So he will be getting 1 as the output of this AND gate 8. And that one, this is OR gate. If one of the input of the OR gate is 1, it is input of this flip flop is 1. Then when you are applying clock, this 1 will be coming as the output of the flip flop 0. Okay. Now during the second clock, this 1 will be coming to the gate 6. So already one of the input of this gate 6 is 1. So it will give an output of 1. Since it is an OR gate, it will give an output of 1 even if one of the input is 1. So during the next clock, what happens means this flip flop will give the output of 1, 1, and that 1 is connected to 4. So this flip flop, this diode, this gate will give an output of 1. This AND gate will give an output of 1, and since one of the input of this OR gate is 1, its output is 1. So during the next clock, it is shifted to here. So to the second gate, second AND gate. The one of the input of this AND gate is 1. So both the inputs are 1. So it gives an output of 1. This is an OR gate. One of the input is 1. So it will give an output of 1 to the input of flip flop 3. So during the next clock pulse, so its data is, it will get during the next clock pulse, we will be getting the output here. Okay, so data is shifted left. Similarly, next we are considering M as 1. So M is equal to 1. The gates 1, 3, 5, 7 are enabled, and the gates 2, 4, 6 and 8 are disabled. So when you're giving one when you're giving 1 here, so when you're giving 1 here, you will be getting 0. So the one of the input of this gates 2, 4, 6, 8 are connected to 0. So since it is AND gate, if one of the input is 1, it output will be 0. So it is disabled. But the gates 1, 3, 5 and 7 is connected to the to 1. So it's one of the input is 1. Now we are giving serial input to this gate 1. So already this input is 1. So since it is AND gate, if both the inputs are 1, you'll be getting an output of 1 here. So this is an OR gate. If one of the input is 1, you'll be getting an output of 1 here. You'll be getting 1 as the output here. Now you are applying clock. So your output will be coming here. During the next clock, this 1 will be coming as an input to this gate 3. Already it's one of the input is 1. So here it is, you'll be getting an output of 1. This is an OR gate. It will give an output of 1 if one of the input is 1. So you'll be having a 1 here. During the next clock, this 1 will be shifted here. So during next next clock, this 1 will be shifted here. Similarly, it will be performing shifting right operation. So when M is equal to 1, it will perform shift right operation. When M is equal to 0, it will perform shift left operation. Okay. So here we are having a control input M. This control input will determine whether it has to perform shift right or shift left. So this is a bidirectional shift register. So it will perform shift right and shift left operations. Okay, so this is a bidirectional shift register. So this is the circuit of universal shift register. So it is having 4:1 mux. So you know that 4:1 mux will be having 2 select lines, 4 inputs and only 1 output. So it is having a 4, it is having 2 select lines, and now this is universal shift register. It is having 4, it is having 4:1 mux, and the mux will be having 2 select lines, 4 inputs and 1 output. Okay, and the circuit is also having 4 D flip flops. So to the input 3, we are providing the parallel inputs. So that the input 3 of the 4:1 mux. So here you are having 4:1 mux. To all the fourth input of all the mux, we are providing parallel inputs. And when you are giving 0, 1, it will perform shift right operation, and it when you are giving 1, 0, it will perform shift left operation, and for 1, 1 parallel load. So it will perform all the operations. So when 0 0 there is no change. When you are providing 0 1 it will perform shift right operation, and 1 0 it will perform shift left operation, and 1 1 it is parallel load. So this universal shift register will act as a serial in, serial out, serial in, parallel out, parallel in, serial out, bidirectional shift register. All the things it will be performing. So this is nothing uh, universal shift register. It will perform all the functions. Okay. Now we are going for the applications of shift register. So the shift registers are used for temporary data storage. It is used for multiplication and division. So you take a number 8. So if you shift one bit right, so you'll be getting 0 1 0 0. So if you perform one bit right shift, then it is nothing but equal to divided by 2. So this is 8, and when you are shifting this right 8 right by one bit, then you are getting 4. That is nothing but divided by 2 it is performing. So division, dividing by 2 it is doing. So then it can be used, this shift register can be used in used as a delay line. So it can be used in ring counter, and it can be used to used in parallel to serial converter. So these are the applications of shift register. Next we are going to see shift register counters. So first we are going to see Johnson counter. Johnson counter is a shift register counter. In Johnson counter, the complement output of the last stage is connected to the input of first stage. So how you are connecting? So in Johnson counter, you are connecting the complement output of the last stage to the input of first stage. Johnson counter will produce a unique sequence of state. It will produce a unique sequence of states. Initially, the output of all the flip-flops are 0. So the complement of the output of the last stage is 1, which is connected as the input to the first stage. So complement of the last stage is nothing but 1. It is connected as the input to the first stage. Now, so during first positive edge, during the first positive edge, the output will be 1 0 0 0. So during the second positive edge, 1 1 0 0 is the output. So it is also called as twisted ring counter or Mobius counter or switch tail counter. This Johnson counter is also called as switch tail counter or Mobius counter or twisted ring counter. So next we are going for, this is 4-bit Johnson counter. Here the complement output of the last stage is connected to the first stage. So you are connected the complement output of last stage to the first stage. So this is the output of, or timing diagram of your Johnson 4-bit Johnson counter. Okay. So initially all the inputs are 0. Inputs are, all the flip flops are 0. Okay. And this is a sequence. First sequence is 1 0 0 0. Next is 1 1 0 0. Next 1 1 1 0. Then 1 1 1 1. Then 0 1 1 1. Then 0 0 1 1. Then 0 0 0 1. Then again the initial condition will repeat. So this is 4-bit Johnson counter. Now this is a sequence. Initially all are 0. Then we are making the first output of the first one as, because the complement output of the last is nothing but 1. So it will be given as an input to the first stage. So the output of the first flip flop will be 1. In the next clock, both the thing will be 1. So next 3 outputs will be 1, and the last one will be 0. Then all the 4 outputs will be 1. Then the first when all the 4 outputs are 1, the complemented output will be 0. That is fed as an input to the first flip-flop. So again, the 0 will repeat up to 0, 0. Again, the condition will repeat. Okay. Then a ring counter. Ring counter is a shift register counter. In ring counter, Q output of the last stage is connected to the input of first stage. So previously, complement output of the last stage is connected. Here, the Q output of the last stage is connected to the input of first stage. In this counter, the output of the first flip-flop is made 1 by using preset, and all the other flip-flops are cleared. So the flip-flop is having two special input. One is called reset, another one is called preset. When you are giving one to, or when you are giving a signal to preset, output of the flip-flop will become 1. And when you are giving input to the reset, the output of your flip-flop will become 0. So the output of the first flip-flop is made 1 by giving input to the reset, and all other flip-flops are cleared. So the first input will be 1 0 0 0. Then during the first positive edge of the clock, the output will be 1100, then 11100, then like that. This is a 4-bit ring counter. We are connecting the Q output to the input, and we are making the output of the first flip-flop as 1. So this is the sequence. Okay, this is ring counter. Next we are going to see the topic modulo n counter in the third unit. So we are going to see the topic modulo n counter. Now, what is modulo n counter? So, counter is nothing but a register capable of counting the number of clock pulses arriving at its clock input. So, modulo n counter counts the clock from 0 to n minus 1. So, steps for design of modulo n counter. So, first we have to determine the number of flip-flops needed. So, here if n represents the number of flip-flop, then 2 to the power n is greater than or equal to number of states in the counter. Choose a type of flip-flop to be used. Then using excitation table for selected flip-flop, determine the excitation table for the counter. So by using the excitation table of flip-flop, we have to find the excitation table for counter. So using K-map, we have to derive the flip-flop input function. So we have to draw the logic diagram. So the steps are, first we have to determine the number of flip-flops needed. So we have to determine the number of flip-flops needed. Then if n represents the number of flip-flops, then 2 to the power n should be greater than or equal to number of states in the counter. Choose the types of flip-flop. Which type of flip-flop you have to use? You have to choose. Then using excitation table for selected flip-flop, determine the excitation table for counter. Use K-map to derive the flip-flop input function. Draw the logic diagram. So first we are going to a design a mod 10 counter, or design a divide by 10 counter, or design a decade counter, or design a BCD counter. So all these questions are having the same answer. So all these questions we are having the, so either it is a mod 10 counter, or divide by 10 counter, or decade counter, or BCD counter. So this answer of these 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 four questions is same. So it is nothing but mod 10 counter means it will count from 0 to 9. So mod 10 counter is a counter which counts the number, not number, the clock, clocks from 0 to 9. So the number of flip-flop needed to implement mod 10 counter is found by the following expression, that is 2 to the power n is greater than n. This n is nothing but 10. So this n is nothing but the 10. So we have to substitute the value of n. So when you put n is equal to 3, you will be getting 8. 8 is not greater than 10. So we are putting n is equal to 4. So 16 is greater than 10. So we need 4 flip-flops to implement this mod 10 counter. So this is the state diagram. So if 0 is the present state, next state is 1. If 1 is the present state, next state is 2. If 2 is the next state, present state, next state is 3. If 3 is the present state, then next state is 4. If 4 is the present state, then next state is 5. Then if 5 is the next state, then the 5 is the present state, then the next state is 6. If 6 is a present state, then next state is 7. If 7 is a present state, the next state is 8. If 8 is a present state, then next state is 9. If 9 is a present state, next state is 0. So this is a state diagram of mod 10 counter. Now we are going for the transition table. So here we need 4 flip-flops to implement this problem. So we are taking 4 variables A, B, C, D, and this is the present state. So in the next state also we are taking 4 variables A1, B1, C1 and D1. So these are the next state variables, and to implement this function, this model 10 counter, we need 4 flip-flops. So we are having we are taking 4 flip-flops. So here in this question they have not mentioned the type of flip-flop, so we are taking T flip-flop. So we are taking 4 flip-flops, TA, TB, TC and TD. Okay, so these are the inputs of 4 flip-flops. Okay, now so from the state diagram we have to fill the present state and next state. So from the state diagram we know that if 0 is a present state, if 0 is a present state, then next state is 1. So if 1 is a next state, then if 1 is a present state, the next state is 2. If 2 is a present state, next state is 3. If 3 is a present state, next state is 4. If 4 is a present state, next state is 5. If 5 is a present state, next state is 6. 6 is a present state, next state is 7. If 7 is a next state, then present state, then next state is 8. If 8 is a present state, then next state is 9. If 9 is a present state, next state is 0. This is mod 10 counter, and it will count from 0 to 9. So for 10, the next state is don't care. Similarly, for 11, it is don't care. For 12, it is don't care. For 13, it is don't care. And for 15, it is don't care. So once again, I am telling how to write this excitation table of counter or transition table of counter. So from the state diagram, we are writing with 4 variables. We are writing first, we are taking the state, first state, that is A, that is 0 0 0 0. If 0 0 0 is the present state, next state is 1. 0 0 0 1. If 1, then 2, 2 3 3 4 5 6 7 8 8 9 9. This point is, you should be clear. Next state of 9 is not 10 but 0. The next state of 9 is 0 and not 10. Similarly, the next state of 10, 11, 12, 13, 14 and 15 is don't care. Okay. Then we have to fill the flip-flop inputs. So in order to fill the flip-flop inputs, we have to check the present state and the next state. In the present state, first you check A and A1. This is T flip-flop. For T flip-flop, the excitation table is for 0, 1 and 1, 0, it is 1. For 0, 0 and 1, 1, it is 0. So for 0, 0, you have to put 0 here. Similarly, for 0, 0, you have to put 0. 0, 0, you have to put 0. For 0, 1, you have to put 1. Similarly, the second one. For 0, 0, 0, 0, 0, 0, 0, 1, 1, then 1, 0, 1. Similarly, here 0, 0, 0, 0, 0, 0, 1 is 0, 0 1 is 1. Now you come to here, 1 first a and a1, 1 x, 1x is x, 0 x is x, 1x is x, 0x is x. So only the present state and next state 0 0 0 1 1 0 and 1 1. If the present state is 1, next state is x, then the input is x. Similarly, if the present state is 0, next state is x, then the input is x. So you have to fill this flip-flop inputs. So we have filled the flip-flop inputs. So after that, here how many flip-flop inputs you are having in TA, TB, TC, TD? 4 flip-flop inputs you are having. 4 T flip-flops. And how many inputs? You have to consider only present state here. We are in this circuit, we are not having any external input. So you have to consider only the present state. So in the present state, you are having 4 variables A, B, C, D. So you have to draw 4 variable K maps. So first, this is excitation table of T flip-flop. By using this only, we are filling this. By using this only, we are filling that excitation table of counter. Now, next one, by this is a K map for TA. We are checking the column of TA and we are plotting the ones and don't cares, and then we are going for grouping. So after grouping, we are writing the expression. Okay, this is the expression. Now again we are going for TB. So we are plotting by looking the column of TB, we are plotting the ones and don't cares, and we are writing the expression. Similarly for TC, we are writing the ones and don't cares, then we are writing the expression. This is for TD. After that, we are going for implementation. So this is the implementation of your mod 10 counter. Here you are having 4 flip-flops TA, TB, TC and TD. And from the expression output flip-flop input expressions, we are drawing this diagram. Okay, the output of this TA is A, and output of TB is B, and output of TC is C, and output of TD is D. From this we are we are drawing the diagram. Next problem, we are going to design a counter with the T flip-flop that goes through the following binary repeated sequence. So the given sequence is 0, 1, 3, 7, 6 and 4. So the counter will repeat in this sequence. Okay. So or this problem can be given in another way. So design a counter which goes through the following sequence, that is 0, then 1, then 3, 7, 6, 4. So first we are going to draw the state diagram. So if first 0, then next it is going to 1, next 3, next 7, then 6, then 4, then 0. This is the state diagram of this given counter. So if 0 is a present state, next state is 1. If 1 is a present state, next state is 3. If 3 is a present state, next state is 7. If 7 is a present state, next state is 6. If 6 is a present state, next state is 4. And if 4 is a present state, next state is 0. So from this state diagram, we have to draw the state table. So here the highest number is 6. So to represent 6, we need 3 bits. So 3 flip-flop is needed to implement this counter. Or in other way, we can find the number of flip-flops. 2 to the power n is greater than n. Here n is nothing but 6. That is highest number is 6. So 2 to the power 3 is greater than 6. So see, 3 flip-flop is needed to implement this problem. Next is we are going for the transition table. Here you are having 3 flip-flops. So and here the highest number is 6. So we need 3 variables, minimum 3 variables to represent 6. So we are writing each number by 3 bits. So if 3, so from the state diagram, if 0 is a present state, the next state is 1. If 1 is a present state, the next state is 3. If 3 is a next state, it is not given. In this problem, they have not given what is the next state of 3. So we are putting it as don't care. So if present state is, sorry, the next state of 2 is not given, so we are putting it as x. Similarly, the present state of, if 3 is a present state, next state is 7. If 4 is a present state, next state is 0. Similarly, the next state of 5 they have not given, so we are putting it as don't care. Similarly, next state of 6 is 4 and next state of 7 is 6. So from the state table, we have completed this transition table or excitation table of counter. Okay. So for the given states, we have mentioned the next states, and the states for which the next states are not mentioned, we have put don't cares. So after that, we have already found out, find that we need 3 flip flops. So unless mentioned, it is better to go for T flip flop or D flip flop. Here I have taken T flip flop. So I have to check the present state and next state. For TA, I have to check A and A1. Both are 0, so 0. From the excitation table of T flip flop, for 0, 1 and 1, 0, we are having 1. And for 0, 0 and 1, 1, we have 0. So present state is 0 and next state is 0. So in the place of TA, we are having 0. So now you check B and B1. Present state is 0, next state is 0, you put TBS 0. Now you check C, present state is 0, next state is 1. So you put 1 in the place of TC. Similarly, you come for the next one, present state is 0, next state is 0 for A. So here it is 0. Similarly, present state is 0, next state 1. So 1 in TB. Present state 1, next state 1 for 0 in TC. Now you come to don't care. 0 in the present state and don't care in the next state. So don't care. 1 in the present state and don't care in the next state. Don't care. 0 in the present state and x in the next state. So don't care. So we have completed the flip-flop inputs. After that, here you are having 3 inputs. And the flip-flop inputs is 3. So you have to draw 3 variable K maps. One for TA, one for TB, and another one for TC. So we have to draw K maps for TA, TB, and TC, and we have to find the input expressions for this TA, TB, and TC. So for the K map, the input variables are A, B, and C. This is excitation table of T flip flop, from which we have found out the input of TA, TB, and TC. So first we are checking the column of TA. We are plotting the ones and don't cares, and then we are grouping, and we are writing the expression. Similarly for TB, we are writing the plotting ones, we are grouping, and then finding the expression. Similarly for TC. Okay. So then implementation. We have implemented by using T flip flop. So we have used T flip flop. This is A, this is B, and C. Flip flop A, B, and C. Okay. Next, so we are going to study what is meant by lockout condition. So in a counter, if the next state of some unused state is again an unused state, and if by chance the counter happens to find itself in the unused state and it never arrived at a used state, then the counter is said to be in lockout condition. So what is lockout condition? So in a counter, if the next state of some unused state, you are having some unused state, and the next state of that unused state is again an unused state, and if by chance, if the counter is going to that unused state, and if it is staying there and it is not coming to the used state, then the counter is said to be in lockout condition. The counter which never goes into lockout condition is called self-starting counter. What is self-starting counter? The counter which is not going to a lockout condition is called self-starting counter. So what is lockout condition? In a counter, if the next state of an unused state is again an unused state, and if by some means if the counter is going to that unused state, and if it is not returning to the used state, and if it is staying there, then it is called, and such a condition is called a lockout condition. And the circuit which is not going to this lockout condition is called, not going to the lockout condition is called self-starting counter. So now we are going to design a counter with the following binary repeated sequence, but the counter should not go into the lockout condition, and the type of counter what we are designing should be a self-starting counter. Okay, so here the highest number is 6, so we need 3 flip-flops. First we are going to draw the state diagram. So this is the state diagram of the given counter. In this 0, 1, 2, 4, 6 are the used state, and the unused states are 3, 5, 7. 3, 5, 7 are the unused states, and 0, 1, 2, 4, 6 are the used states. Now, if by some means, if the counter is going to the unused state, we have to force that um, uh, counter to come into the next used state. So if it is going to the 3, here the unused states are 3, 5 and 7. If by some means if the counter is going to 3, then we have to force it to come to 4. Similarly, if it is going to 5, we have to force it to come to 6. Similarly, if it is going to 7, we have to force it to come to 0. So next we are going to draw the state diagram in which we are forcing the, so from this state diagram we understand that 0, if 0 is a present state, next it will be going to 1. If 1 is a present state, it will be going to 2. If 2 is a present state, it will be going to 4. So if some means if it is going to 3, we have to push it to 4. Similarly, if 4 is a present state, we have to go to 6. If some means if it is going to 5, we have to push it to 6. If 6 is a present state, it will go to 0. By some means if it is going to 7, we have to push it to 0. So this is nothing but a self-starting counter. So number of flip-flops needed is 3. So by the equation 2 to the power n is greater than or equal to capital N. So we are finding the number of flip-flops. Then we are going for the transition table. So since we are having 3 variables, we can write from 0 to 0 to 7. So from the state diagram, so we are going to write the state table. So 0 is a present state. So from the state diagram, if 0 is a present state, next state is 1. So if 1 is a present state, next state is 2. If 2 is a present state, next state is 4. But 3 is an unused state. So 3 is a unused state. So if it is going, if our counter is going to 3, then we have to force it to come to 4. So if 4 is a present state, the next state is 6. Similarly, 5 is a unused state. If our counter is going to 5, we have to make it to 6. Then if 6 is a present state, next state is 0. Similarly, 7 is an unused state. If it is going to 7, if our counter is going to 7, then we have to force it to come to 0. The main difference between the previous problem and this problem is, in the previous one, in the place of unused state, we have put down chaos. Here we are making it to come to some used state. So here I am doing it by using D flip flop. So D flip flop, we know that D input D is equal to next state. So DA is nothing but A1. Just you copy A1 to DA. Similarly, DB is nothing but I copy B1. DC is nothing but C1. Just I copy C1. Next here you are having three flip flops, that is DA, DB and DC. So and three inputs DA, DB and DC, and you have to draw three K maps, and the number of variables is 3, A, B and C. After that, we are checking the column of DA, DB and DC, and we are writing, or we are plotting the ones, and we are grouping, and we are writing the expression. Similarly for DB and for DC. Then we are implementing by using D flip flop. So here the type of flip flop we've used is D flip flops. Unless mentioned, it is better to go for D or T. So because number of flip flops you have to draw is getting reduced. So if you go for JK or SR, you have to draw more number of flip flops. So it is better to go for D or T.